All right, well, here comes our first video presentation other than the introduction, and we start to get into the material. We start off with one-dimensional motion, and you should in front of you now have the one-dimensional motion PowerPoint problems in front of you. This way you don't have to write out the problems later. They're already there for you. There's no note outline for the rest of this, but I recommend that you take some notes. This way you have something to go back to. Of course, you can watch this video as many times as you want. No limitations there. All right, well, we start off by talking about what they call kinematics. And kinematics is just a description of motion. So it really just describes what happens. And in that description, a lot of things can be determined, as you're going to find out. But we'll start off with classical mechanics. Kinematics is what we're starting off with. Pretty standard starting point for a physics class. All right, so if you're going to describe motion, maybe you want to describe distance. How far did something go? There is, we've talked about the meter. What does a meter mean to us here in the United States? Well, it's a little over 3 feet. About a yardstick is close to a meter anyway. And a kilometer is a little bit less than a mile. So when we talk about these things, good idea to know with our description of motion what we might be talking about. Well, other than distance, there's a term called displacement that is similar. They both start with a D, of course, but displacement is your change in position. How far are you from a starting point? So here is a track that is 400 meters long, right? So if you go around the track one time, you have completed 400 meters worth of distance. But you're right back to where you started from. And there's the distinction between distance and displacement. So one lap is 400 meters. 400 meters is your distance. I think I just said this. And the displacement would be 0 meters. You're right back at your starting point. So hopefully that emphasizes the idea. All right, well, speed. How fast are you going? That might be a pretty good description of what's going on as well. And that's going to be how much distance you cover and how much time. So distance and time are now related together when you talk about speed, and certainly another convenient way to describe motion. So we can talk about speed as being the distance, the change in the distance, over the change in time. How much distance, how much time. All right, so symbolically we can represent this with the deltas. Those little triangles there mean a change in. So a change in distance over a change in time is a way of symbolically representing speed. Okay, so things can be going very fast, we know that. Things can be going very slow. We're going to be measuring all kinds of different speeds. Just to give you an idea, 1 mile per hour is roughly 0.45 meters per second. We're going to deal in meters per second a lot. If you double meters per second, you have a rough idea of what the miles per hour are. The bigger the number, the more off you are, but it'll give you a rough idea in miles per hour what the meters per second mean. Okay, and 1 mile per hour is like going almost, a little over 1.5 kilometers per hour. And that might not matter to us too much now, good point of information, but if you ever go somewhere where the speed limits are in kilometers per hour, it might make a difference to you. Okay, so let's see. Speed, then, we can say is distance divided by time, and another way that we can symbolically represent it is by using the V for speed. Any ideas why we use a V for speed? More on that story later. But speed is equal to distance divided by time. Or we could say distance is equal to speed multiplied by time, and we start having our symbols that are very similar to what I showed you in that formula sheet in the introductory video. D is equal to VT is a useful formula, but you won't find it in the formula sheet. They really have the idea that you'll understand that. It's the most basic kinematic equation. Okay. Now, since we're talking basics here, what has to be true about the speed if this equation is going to work? Well, think about it. Pause the video if you like, and then you can go back to it. If you said that it must be constant or an average speed, then you're already doing some nice thinking, making some pretty good connections there. Yeah, the constant one is pretty obvious, but the average as well. Very rarely does an object go at the same speed, but it's very convenient to talk about its average speed. This is different than instantaneous speed. The average is going to be the collection of all these different speeds together. The instantaneous speed, as the name implies, is how fast it's going right at that instant. We'll see how this is represented on a graph later on when we do the graphical representation of motion. All right, so a speedometer on a car is going to give you your instantaneous speed. Can you think of something else that would? Now, these days the GPSs are pretty good at that too. Tell you how fast you're going, and they'll use that to make some calculations too about when you might get to where you're trying to get to. Okay, so let's start with our first problem here, and you will find this on your 1D motion PowerPoint problems form that I had printed out for you. This way you don't have to write these problems out again. But this is a very basic kind of problem here, but I'm going to use it to illustrate how we're going to be presenting our problems all year long. So, to start off with, you're going to identify the information. The V, have you figured out why speed is used, a V is used for speed yet? More on that story later. But the speed here is 20 meters per second, and I want to represent that to a person who's looking at my problem and how I've gone about solving it. An important part of this class, as I've already mentioned, is being able to explain your work. A clarity of presentation is what we'll be looking for. So in this particular problem, there's an average speed of 20 meters per second and a time of 5 seconds, and the question is, how far does it go? So I am over here indicating the material that I know, the information that I know symbolically, and also the thing that I'm looking for as well. Okay, in formula terms, I can use D is equal to VT, and I'm all set to plug it right in now. So when I plug in my numbers, the units are important as well, in as much as you're doing the math on the numbers as well as the units. So here seconds cancel out, and you're left with a distance of 100 meters. Okay, a very basic problem here, at least I hope it was for you, but I'm using it to illustrate the points that we are going to identify the variables and show the work for every single problem, even and maybe especially when they start getting complicated. It's important for you to be clear in your thought process and for me to be able to understand your thought process as well. And if you're taking the AP exam, it'll be important for them to understand your thought process as well. So we're going to all start off symbolically on the same page. So we're going to always identify the variables and then show the work. Now, you can have in your mind how to do it. Show me the correct answer. You're not going to get full credit for just showing me the answer, and they won't do that on the AP exam either. There's things that are expected here in the presentation. And we'll start with that from our very first problem. And you know what? We already did. Okay, so let's see. Here's another problem here. And I'm going to give you a chance to try to sort this one out. So give yourself a chance. Don't worry, if you have problems, we can talk about it in class. So go ahead, hit the pause button, figure it out, write it down. You're not going to just wait for the answer, are you? Well, how would I know? But at any rate, when you're done, the answer you should get is, sorry, jumped the gun a little bit there. All right, so let's identify the information again, the 50 meters per second, the distance of 625 meters, and the time that we're looking for. So with D is equal to VT, we can arrange this to solve for time. And a big part of what we're looking for on the AP test is the idea of manipulating variables. So here there's strength in manipulating the variables before you plug in and show your work, which would be this last step here, which would give you 12.5 seconds. So 50 meters per second, roughly 100 miles per hour. Are you seeing beyond the problem and trying to picture what's going on? That's what I would always encourage you to do. So for example, what kind of object would it be that could do this? That could go at about 100 miles per hour for 12.5 seconds. What is the object? Well, I guess there's a lot of correct answers, but it could be a cheetah. They go pretty fast. Look at this one go. Ooh! All right. Well, let's move on a little bit here and see what we got going on. How did you do? Did you pause it and then was your solution the same as mine? Well, okay, maybe not the Cheeto. All right, so here we go, because now we want to talk about the idea of being able to change speeds. An average speed doesn't take into account in detail how the speed is changing, but acceleration. That's going to be talking about how fast speed is changing. So we introduce a new concept here, acceleration, although it's probably familiar to you already. Okay, so acceleration is going to be the change in speed over the change in time. How fast does the change in speed happen? That's really what acceleration is. With our delta symbols for change, we can represent it now as change in speed over change in time. Okay, and if I shuffle that around a little bit, I could now add in the letter A for acceleration to add another symbol into the mix here. Okay, a change in anything is going to be where you ended up minus where you started. So now we want to start making a distinction between where we ended up and where we started. So a change in speed, the final speed minus the initial speed, can be represented with the V over here for final, and you'll see that on your formula sheets as well, and the VO, which means V naught or V initial. So that means the beginning speed that we're talking about. You won't always start from rest. Sometimes you'll already be up and running, and it's important to be able to distinguish between your final speed and the speed you started at, especially when talking about acceleration. Okay, so I could now say, in adding these symbols in, that acceleration is V final minus V initial divided by the time. And there's my acceleration equation. Okay, so here's another one. Please pause now and figure this one out. See what's going on. What is the acceleration of the object given these circumstances? All right. Well, this time, hopefully you paused and tried. And this time I don't think I have it worked out all the way. I just have the answer for you. So 4 meters per second squared should be the answer. Once again, what kind of object could do that, right? What kind of object would be going 4 meters per second faster every single second? 8 miles per hour faster for 5 seconds. What was the object? Can you picture it? Can you make a connection? Hey, how about this? How about, there it is, my first car, a 1973 Ford Gran Torino. Oh, that car was something. That car could do that. Okay, ooh, go. Well, all right. It turns out we have to stop there, so that'll be the end of part 1 for one-dimensional motion. Please tune in for part 2 of one-dimensional motion.